Okay, the session will resume in English. As we all know, large language models are revolutionizing AI. They keep improving with more data and computation. Unlike past deep learning, large models are general technologies that can be prompted to perform various tasks and may eventually reason. This is changing AI frontiers, altering how companies operate and researcher careers. In our next session, we will have our first roundtable discussion for today's annual conference. We will have on the topic of the renaissance of large language models, paradigms, and challenges. Let us first welcome roundtable discussants to join us on stage. At this time, I'm very honored to introduce our discussants. Our keynote speaker will be Jason Wei. He will join us virtually. Jason Wei is an AI researcher living in San Francisco. He currently works at OpenAI. Previously, he was a senior research scientist at Google Brain, where he popularized chain of thought prompting, co-led the first efforts on instruction tuning, and wrote about emergence in large language model. Let us first welcome Jason Wei to give his keynote speech. Hi, Jason, can you hear me?
Hey, can you hear me? Okay, I will share my screen now. Yeah, thanks so much for inviting me here today and for the nice introduction. I'm going to talk about a trend that we've seen recently in large language models called emergent abilities. So here's a bit of the structure for the first part of the talk. So I'll first go over the framework for thinking about large language models, which involve scaling laws and emergent abilities. Second, I'll talk about a number of different types of emergent abilities, including emergence in few-shot prompting, U-shaped scaling, chain of thought, RLHF, and calibration. And then finally, I'll conclude with some discussion, which includes additional ways to unlock emergence other than scale, different metrics for examining emergence, and the implications of emergence. So let's talk about scaling first. And I'd like to take a second to appreciate how far we've come with taking this concept of scaling. So here's a simple plot of time on the x-axis, and then compute on the y-axis. And crucially, this compute is in a log scale, and we can measure it in a number of flops for training a language model. So first we see BERT large here in 2018, which takes 16 V100 GPUs for 33 hours. Not that much, but also not nothing. In 2019, we had T5, 11 billion. In 2019, we had T5, 11 billion, which is about 100 times the compute of BERT large. In 2020, we had GPT-3, which is about 1,000 times BERT large. And then in 2022, we had PaLM, which takes 6K TPU V4s for 2 months. And the training cost for this is in the millions of dollars for sure. So the analogy that I like to use here is to recall like the concept of moles from chemistry, which you might have learned in high school, which is the number of atoms in 12 milligrams of carbon-12. So 6e, 6 times 10 to the 26th. And I remember my teacher talking about how big that number is and like, don't even try to imagine it. But the flops that we put through these TPUs is larger than this unit of measure moles. And let's talk about the reason we still did scaling, given that it's so hard, which is scaling laws. And the idea of scaling laws is basically described in this plot. So you have compute on the x-axis and test loss on the y-axis. And here the loss is measured on a very general corpus of text, and lower is better. And so the main point is, as you increase the amount of compute used to train your model, the loss is expected to go down in a smooth and predictable fashion. The scaling laws paper puts it nicely. Language model performance improves smoothly as we increase the model size, dataset size, and amount of compute for training. And the caveat here is that the training isn't bottlenecked by either of these factors. And my rephrase of this is simply, you should expect to get a better language model if you scale up compute. And the reason this is actually called a law is that if you look at the x-axis, you can see that it spans 7 orders of magnitude, which means that it's pretty likely that the trend will continue, and you'll get a predictable improvement in performance. So in other words, it would be pretty surprising if the loss started to plateau as you scaled more compute. As an example of how predictable performance improvements from scaling can be, here's a plot from the GPT-4 paper. Again, the x-axis is compute. Here, the y-axis is slightly different. It doesn't say, or here the x-axis is slightly different. It doesn't say exactly how much compute, but it plots it in terms of GPT-4 compute. And the y-axis is, again, the loss here on the OpenAI codebase. And so what we see is that you can plot a relatively smooth curve over all these models. And if you continue tracing the curve, you can predict the loss of GPT-4. And the crucial point is basically, you can predict this loss. To predict the loss, you only need to train models of up to 10,000 times less compute than GPT-4. So usually scaling laws focuses on broad evaluations like perplexity. And we also want to see how the scaling behavior looks for downstream tasks. So there's this corpus called Big Bench, which compiled 200 downstream tasks. And if you look at the scaling behavior for them, you'll see that some tasks scale very smoothly, so they're very predictable. But the interesting thing is, this is only a relatively small fraction of the tasks, 29%. What are the other tasks? Well, 22% of the tasks are flat, so the model never does better than random. A small percent of the tasks are inverse scaling, which means that performance gets worse with scale. Some tasks are not correlated with the scale, 13%. And this final category is what we'll talk about, which is called emergent abilities, for which the performance is mostly flat, and then past some model threshold, it spikes to become much better than all the previous models. And so some people have been talking about emergence on Twitter. So I guess it's good to be specific about what emergence means in this context. I don't mean emergence in the sense that AI has some agency or that the AI advancements are created by AI. But emergence has this scientific meaning, which is a qualitative change that arises from quantitative changes. Some people like to call it a phase shift. And the idea of emergence dates back to this 1972 piece by Nobel Prize-winning physicist P.W. Anderson. And since then, it's been well studied in science. I like to give 2 examples. So one is, with a bit of uranium, nothing special happens. With a large amount of uranium, you get a nuclear reaction. Another example is, given small molecules such as calcium, you can't meaningfully encode useful information. But given larger molecules such as DNA, you can encode a genome. Now, for large language models, we had a position piece where we proposed the definition of emergent abilities for large language models. An ability is emergent if it is not present in smaller models, but is present in larger models. And there's a natural question of how to quantify smaller models. You can do it by either model size, amount of training data, or training compute, which is the product of both. We'll look at emergence through the lens of training compute, but you'll get similar plots for most models if you just use model size. And a good caveat is that this isn't everything that goes into the model. Other things like data quality, optimization objective, etc., also matters, but I think the phenomena of emergence holds nonetheless. The first type of emergence I'm going to talk about is emergence in the few-shot prompted setting. If you're not familiar with how the few-shot prompted setting works, basically the language model is a next word predictor. And the way we can prompt it is by appending a few examples of an input-output pair. In this example, the input is a movie review, the output is the sentiment. And then we ask the language model to predict the next word for the target. And our definition of emergence in the few-shot prompted setting is a language model ability is emergent if it is about random. Sorry, there's a typo. If it's about random for small models, but well above random for larger models. And so here are a few plots from various papers where we see the emergent behavior. So the x-axis is scale, measured in compute, training flops. And then the y-axis is the performance on the task. You can use various metrics like accuracy, blue, etc. And then the point here is that you can see the performance is flat for small models, about random. And then past some certain model size, the performance spikes to well above random. So if you naively try to extrapolate the data points from the small model, you'd actually conclude that the large model probably wouldn't be able to do the task. An open question is whether it's possible to predict emergence using only smaller model sizes. To be a bit more concrete, here are a few examples. So this is a multi-task natural language understanding task called MMLU. And it's basically a compilation of high school to professional level exams. This happens to be a math question. And the model has to pick the answer from 4 options. And as you can see, for the models here, the performance only becomes above random when the model is trained with something like 10 to the 24 training flops. Here's another example from the Big Bench benchmark, where the model takes in an input sentence and then has to give the international phonetic alphabet translation. And here the performance is measured in blue, which is a word matching metric. And you can again see that you have to go past 10 to the 22 flops to get better than random performance on this task. And to sort of give an example of how this emergence happens, I made this very simple example using the OpenAI API. So here's a simple translation task where the model is supposed to translate this sentence to Spanish. And so you might have a plot like this where the x-axis is model scale and the y-axis is performance, say blue score. And then you have, there's 0. And then you have this behavior where the performance is 0 for 2 small models, and it's something high for the larger models. And when you look at the outputs, you can get some insights into what's happening here. So the smallest model, Ada, just doesn't understand the task and just repeats the sentence. Then you go to the middle model, Babbage. It still doesn't understand the task and also just repeats the sentence. And then finally, you can see that Curie does the translation perfectly and gets the task 100% correct. Now, this is just a single example, but it shows that the transition from not understanding the task to doing the task perfectly, it's a pretty good example of that. And if you tried extrapolating the behavior of Ada and Babbage, you might predict that Curie never learns the task. Another interesting result that I want to talk about is from a separate paper that we put out recently. And basically, there was this inverse scaling prize where people try to come up with benchmarks for which model performance got worse with scale. And this is called inverse scaling. And some of the tasks ended up being like this one. So you have this task where the model has to repeat the sentence back, but the sentence is kind of altered to be a little bit tricky. And so here the example is the model has to repeat all that glisters is not glib. And so you'll see the small model gets basically perfect accuracy because it doesn't know the quote, all that glisters is not gold. So it actually does it correctly. And then the medium model actually gets worse because it knows the quote, all that glisters is not gold, and it kind of wants to say that, and it doesn't know how to understand the instruction, repeat my sentences back to me. And the thing that we showed in this paper is if you take an even larger language model, then the performance can actually start to increase again. And basically, the large language model knows the quote, all that glisters is not gold, but it's better at understanding the instruction of repeating the sentence back. And it can actually get perfect performance on this task. And the implication of this is that just because model performance decreases with scale for a given task, doesn't mean it can't go back up again if you keep increasing the model size. Here's a little cartoon that I made to sort of show the implications of emergence. You can consider the x-axis is scale again, and then the y-axis is this sort of imaginary spectrum of things that language models can do. And what the blue shaded part represents is, as you scale up the size of the language model, it can sort of do more things along this range of potential tasks. And you can take some arbitrary model size. This is just an example, 100 billion parameters. And there'll be some tasks that models larger than that will be able to do, but models smaller than that can't do. So in addition to the few-shot prompting techniques, where specific NLP tasks are given to the model, there's a second type of emergence that we call emergent prompting techniques. The idea with emergent prompting techniques is it's a special way of prompting that only improves performance for a large enough model. So if you try it on a small model, it hurts performance, but with a large enough model, it helps performance. Here's one of the primary ways, examples of emergent prompting techniques. So last year we had a paper about chain of thought prompting, which was a way to get language models to do reasoning. And so the previous way you would do reasoning is you'd have a question and then an answer, and then you'd ask a model to an unseen input. So here it's a math question. And unfortunately, the model gets it wrong. With chain of thought prompting, you also start with a question and an answer. But before the final answer, you give the chain of thought, which is this kind of reasoning that you would use to get to the final answer. So like when your teacher at school will tell you to show your work. With this simple modification, the model is encouraged to give the reasoning for the unseen question before giving the final answer. And in this case, it allows it to get it correct. I'll briefly summarize an empirical result here. So we had this paper where we looked at 23 challenging tasks in Big Bench. Here's an example of one of these tasks called Navigate, where the prompt is something like, if you follow these instructions, do you return to the starting point? Turn left, turn right, take 5 steps, take 4 steps, turn around, take 9 steps. And then to solve this, we can use chain of thought prompting to get the model to track the state across each step in the process, and then give the final answer. And then as a result, you can look at the performance delta between the model and the average human rater. So this plot shows standard prompting without chain of thought. And the way that you read it is the red bars are when the model is worse than the average human rater. And the blue bars is when the model is better. And you can see the model loses on most tasks for standard prompting. And then you can use chain of thought prompting, and you see there's a pretty significant shift. The model wins on most of the tasks when you use chain of thought prompting. And here's an example of how chain of thought prompting is an emergent ability of scale. So again, here on the x-axis, we have model scale. And on the y-axis is the average performance on these challenging benchmarks. And you have 2 lines, no chain of thought and chain of thought. No chain of thought is in gray. And you can see for the small models, chain of thought actually hurts performance. So the natural question here is why. When you have a small model, say you have a prompt that the model has to do some reasoning and then answer. When you try to get the small model to do chain of thought, it just doesn't really know what to do, and it isn't good enough at logical reasoning. So it does worse than if you prompted it to just guess a number. And then if you try the large model, it actually reasons successfully, and it has higher performance than if you asked it to give a number straight away. So this is an example of a technique where for small models, performance is hurt, and then large models, performance is better with the technique. And to expand on the cartoon I just showed earlier, you can think of blue as some range of tasks you can do with standard prompting. And then if you use chain of thought prompting, you can increase the spectrum of tasks that the model is able to do. I'll give 2 more examples of emergent prompting techniques. So the one shown here is RLHF, which stands for reinforcement learning with human feedback, which is a technique used in ChatGPT. And the evaluation here is that the blue line is a language model without RLHF, and the orange line is a language model with RLHF. So you can see for the small model sizes, the RLHF model is worse than the baseline. And then for the larger model sizes in orange, RLHF does better than the baseline. And we don't know exactly why this is, but maybe one hypothesis is that the smaller models have to use up all their capacity to learn the RLHF data, whereas larger language models have enough capacity to generalize to unseen things after RLHF. Here's another example of a prompting technique that works better as you scale. So you can look at two of the things here. So this is a measure of calibration. Calibration is basically whether the model knows what it doesn't know. And one way of doing it is you can just look at the probabilities in a multiple choice question of the correct answer. And that's shown in the blue line. And then in the gray line, which is the emergent ability, this one here, you can do a different type of formatting where the language model is given a question and then an option, and then it just says whether the option is true or false. And then for the first 3 points on the gray line, you can see it doesn't really get any better as you scale. But then when you get to the last point on the gray line, you see that the calibration actually is the best when you use the language model using true or false formatting. Oh, and here lower is better. So that's why the gray line is better in an emergent prompting ability. So I wanted to move on to some discussion of emergence. And here's one of the first points I wanted to make, which is that you don't necessarily need scale to get emergence. You can shift the emergent trend line, the scaling curve of emergence, by doing different things to your models. So here's one example. You can see in blue is Palm. And on this particular task, which is classifying geometric shape, it doesn't really do super well. But Palm is trained on a traditional autoregressive language modeling objective. And if we switch up to a better language modeling objective called UL2, we can actually increase, this was shown in a paper published by Google, you can increase the performance by a pretty large amount without increasing the cost of compute. So you can see you use the same amount of compute, but with a different objective, you can get this sort of emergent performance on this particular task. Here's another example of how to get emergence without increasing the amount of compute. This example is from Big Bench. And you can see here that we have like Lambda and GPT-3 models that actually don't really get performance above random. That's shown in orange for this particular task. But then you can use the Palm model, which is actually smaller. And then that Palm model gets much better than random performance. And we don't know the exact reason why, but one running hypothesis is that Palm had higher data quality than Lambda. And so that means if you train with higher quality data, you might be able to unlock emergence without increasing the scale or compute. I want to talk about a few things regarding whether emergent abilities still hold if you change some of the features we use to plot them. So the first potential argument against emergence is that we plot the x-axis using log scale. We use log scale because when we scale up language models, we sort of scale them up in a log fashion. And so you'll get more points on the curve, like more uniformly spaced if you do that. And the argument is if you change it to linear scale, maybe now it's not emergent anymore. But I don't think that's true. So here's an example. So here you can see the emergence occurs at 13 billion, the second to the rightmost point. Basically, it's clear you wouldn't be able to predict that emergence if you had, even if you had plotted the plot differently. The data is still the same. Another potential thing to note is that you could argue that you might want to plot the y-axis also on a log scale. So we plotted it on a linear scale, and it looks emergent. And if you wanted to have your plot be log-log, you could still have the same plot, and here it would still be emergent. And then another point is maybe the final downstream metric of accuracy or error rate is emergent. So it's error rate's about 100, and then suddenly it's much less than 100. But then maybe the cross entropy loss or the logits are actually smoothly scaling. But it turns out that's really not true either for all tasks. So here, example of 3 tasks. And you can see the cross entropy loss does get better smoothly, but there's still a significant bump in the emergent behavior. And I don't think it's immediately clear how to predict this emergence just based on the cross entropy loss. And then finally, we want to make sure that emergence isn't just specific to a particular metric that is very strict. And so you can look at a bunch of different metrics for generative tasks. So we have like scores like Rouge and Bleuert. And you can see that you still get this emergent spike in performance as you scale up to a certain model size. Okay, so I like to say that there's sort of 3 important implications of emergence. The first is that emergence cannot be predicted just by extrapolating scaling curves from smaller models. And so the scaling laws don't actually predict downstream tasks. You might be able to do better than what the curve predicts. The second important thing is that emergent abilities are sort of not intentional in that the trainer of the language model doesn't explicitly specify them. It's just trained on next word prediction. I think an interesting question here is, in the history of deep learning, has this been true before, that AI could do tasks that weren't specified by the trainer of the model? And finally, emergence signifies a shift to single models performing many tasks. Whereas in a previous era, we had lots of models floating around, each of which would do different tasks. So there's an important implication that further scaling can also be expected to elicit more abilities. A good question to think about here is whether scaling might unlock any undesirable phenomena. I'll end with a slide on how emergent abilities have affected the nature of AI work. So back in the day, we would have a few benchmarks, and we would use these benchmarks for many years. Those who have been around will remember using CFAR, ImageNet, or the average score of some benchmark suite. It was pretty easy to rank models. So you just look at a single number, for example, the top 1 accuracy of ImageNet. And then finally, the main training paradigm was to have these task-specific architectures, data, and protocols where you could change the entire ML pipeline based on what task you'd be trying to perform. Now there's this paradigm shift where a single model can perform many tasks without the task being explicitly specified at pre-training. And because of this, the situation is pretty different. Now models saturate benchmarks very quickly, so we need to create new benchmarks all the time. Because these models can perform lots of tasks without specifically fine-tuning on them, the next language model could just saturate an entire suite of benchmarks. The multitask nature of these models also makes them pretty hard to evaluate. So they can do a lot of long-form generation tasks, and often one model that's better at one task is not better at another task. And there's so many tasks that's hard to say that one model is definitely better than another. And then finally, instead of creating architectures, data, and protocol to fit a single task, many companies now focus on training language models as general technologies. So maybe they have some ideas in mind for a downstream task, but it's relatively easy to pivot if something doesn't work out. So to wrap up, thanks for listening to the talk. You can find me on Twitter, and I would also love to get your feedback on this talk at tinyurl.com/jasonwei. So I will end here, and thanks for listening.
Thank you so much, Jason, for the most insightful and wonderful, fruitful talk. We will now go into the roundtable session. Let me first introduce our roundtable discussion, and please stay, Jason, don't walk away. Okay, let us welcome the roundtable discussants to join us on stage. And they are Professor Zhang Jiang from School of System Science, Beijing Normal University. He's also the founder of Swarma Club. His major research interests include automated modeling of complex systems, machine learning on complex networks, open flow networks, scaling analysis, and etc. Ms. Yanran Li, she's the lecturer at Swarma Campus, core member of Swarma Club, former senior algorithm engineer at Xiaomi AI Lab, and research head, R&D head of conversational AI team. Her research focuses on human-machine conversation, generative pre-trained models, and bio-inspired intelligence. Our third discussant is Richard. He's the tech co-founder of Baitruan AI, and he's also the doctoral student of Tsinghua University Innovative Talents Promotion Project. And we will also welcome our next discussant, who is Ziming Liu. He's the doctoral student in the Department of Physics at Massachusetts Institute of Technology, supervised by Max Techpark. His research interests are AI for physics and physics for AI. Ziming will join us virtually, so everybody has already seen his face on the screen. Our moderator for this session is Dr. Chao Lu. Chao Lu is the head of causal AI team at Shanghai AI Lab. He got his PhD in machine learning from University of Cambridge. His main research interests are in machine learning, particularly in causal inference, Bayesian reasoning, reinforcement learning, and deep learning. And he would like to apply them to solve real-world problems in domains like computer vision and healthcare. Okay, Chao, now the stage is yours.
Okay, thank you for the host for introducing our esteemed panelists, and also thanks Jason Wei for the insightful presentations. Actually, this is my second time to listen to your talk, because you gave the same presentations in our lab a few weeks ago. So I think you set a very good stage for today's roundtable discussions on the renaissance of the large language models from the new paradigm and the challenges. So I think it's a good time to start our roundtable discussion. But to kick things off, I think ask the questions to each of the panelists. So what do you see the Jason's findings to connecting to your own researchers or observations in your own fields? So maybe Richard, you can go first, because you also done a lot of work in your companies about the large language models and also observe some emergence abilities on these large language models.
Okay, glad to attend this roundtable and the insightful talk of the Jason Wei. So I want to talk about the emergent abilities. Actually, I always has a question hunting me is what about the emergent ability? Is the matrix is now don't has the much resolution, and the metric can evaluate when the model from the smaller size to the larger size. So I always think about how we can, design a matrix that can be has the more resolution to evaluate the model capability. So yeah. That's my thinking about this. Yeah. So, Yela.
Okay, thank you very much. And in my opinion, maybe most interesting is that we are going more close to see how we can raise the emergencies in the language models, such as we now maybe guess that the code in the data or will raise the reasoning abilities in the language models. And now we also can see that the modularities and the sparsities can be seen or can be detected in the trained large language models, which has not been seen in the smaller language models. So maybe we are closer to detect or to close up that how the emergencies will raise up. So this is now what I'm very interested in, and this is very close to today's discussions. Thank you.
Actually, emergence is a kind of a phenomenon that we can observe in lots of complex systems. But I found that actually when we say the large model has some emergent abilities, I found that it is different from the emergence in complex system. Because it describes that a kind of ability can emerge suddenly when we increase the number of parameters. So I just wonder if there are some similarities or some relations between the emergence of a complex system and the emergent abilities in that language model. Yeah, that's my questions.
Okay, so maybe Ziming also give some comments on this point because it has done some intersection researches between the physics and the machine learning, and also in physics you also have some emergence phenomena you can observe a lot, right?
Yeah, sure. Yeah. So the thing that I found most fascinating is probably neuroscaling laws. Like in physics, you have all sorts of critical phenomenon, like the correlation function is kind of this kind of a power law. And like neuroscientists also argue that like critical phenomenon is the key for your brain, like for intelligence to emerge. So yeah, it's very fun to look at like the analogy here, like the critical phenomenon, like also the analogy to intelligence. And also like the neuroscaling law is something continuous. And I'm also wondering like how the discrete structures like emerge from just training this giant neural network continuously via, SGD or some like SGD based optimizers. And these discrete structures might be like the basis of structures for those emergent abilities, and also how this. So Max mentioned this our quantization work. So in that work we called it quanta. So basically a subnetwork that's responsible for certain function, and we believe that natural languages is actually a very complicated composite task, which you need many subtasks, many abilities to compose, to like maybe compose in a very complicated way. So like neuroscaling law is something that looks continuous, but like the discrete structure is something more discrete and emergent. So how these two worlds, the continuous world and the discrete world, are bridged. And that's something we're really curious about and want to know if there are some physics or mechanism underlying them. That would be perfect. So yeah, that's my take.
Okay, I think a key question about emergent ability is how to measure it, right? So suggestion way, maybe you have some comment on this point, because in recent work we only see the people measure such emergent abilities only in the downstream tasks, right? So measure the performance on different tasks. But how can we, can develop some formal way to measure such emergent abilities without do some, experiments on the downstream tasks? So I think the best way is you can calculate some properties of the mathematical properties. Given the parameters of the large language models, it can just predict if it has the emergence abilities or not.
Yeah, that's a great question. I'm pretty skeptical about theory having any real significance on our ability to predict emergence. I think stuff like the data quality, for example, or what sources of data you train a language model on, are really important for emergence. And I think it's hard to account for that with using theory to try to predict emergence. One thing that I think is sort of people haven't really understood about emergence is that there are things that you predict that don't work well today, but might work well later. And you should sort of assume that some things might get better in the future, even if they don't work today. Basically, what I'm saying is people shouldn't constrain themselves to what tasks the current state-of-the-art language models can do, and they can do their research in prediction of future abilities potentially emerging.
Okay, so I think so Professor Zhang also can come on this point, because in the causal emergence, we have some entropies can calculate some properties about how to measure this kind of emergencies, right? So maybe you also can give some detailed discussion on this point.
Okay, so actually, because I just do some research about the complex systems, and also recently, actually, there's a theory is called causal emergence. In this theory, actually, we can quantify emergence, the degree of emergence of a complex system. The basic idea is when we observe a kind of complex system, actually, we have two levels of the description. One level is in macro level. Another one is bigger and macro level. When the macro levels causality and a kind of degree of causal effect is larger than the macro level, then we can say causal emergence occurs in the system. So I just wonder if we can apply this kind of theory and this kind of quantification to describe the emergent abilities in large language model. But basically, before that, we must find the correspondence between the emergent ability in large models and the emergence of the complex system. Yeah, that's the basic idea of causal emergence.
So maybe we can move to the next questions of the Jason. We also just mentioned the key questions in large language models is which part is unpredictable, which part is predictable, right? So I think so because in another work given by the Craig Young, he has done some researches on mathematics, how to tune the hyperparameters of the large language models, right? It's more efficiently. He observed some, it's a phenomenon. So some hyperparameters is invariant between the small models and the large language models. So it also can prove some theoretical proof to prove this comment. And then he used this theoretical result and tuning the hyperparameters in small number, the models, then directly transfer the value, the hyperparameter values like the learning rate to the larger models. So I just think this is a good inspiration to we can imply which parts of the models can be predictable in the large language models, which part is not. Maybe the performance is hard to predict, but still have some parameters or the hyperparameters can be predicted. Right, so maybe this is the key things. How can training the large language model is more efficient from this perspective? So what do you think, Jason Wei, about this point?
Yeah, that's a really great work. I'm actually really excited for more work that tries to predict emergent abilities. We tried it a little bit in our paper, and it wasn't very easy. But I think it's definitely possible that we can make pretty good guesses at what next abilities will emerge based on the data points that we have from existing large language models. Yeah, I think it's definitely like still an open question of how to predict all the things that we get as we scale up language models, but I'm really excited for more people to continue working on this direction.
So maybe Ziming also can comment on this, because I think it's also quite related to your work, right? So it's quite a theoretical work to build the bridge between the machine learning and the math and the physics.
Yeah, sure. I'd like to bring in some physics flavor to the discussion. There are like theoretical physicists try to use mean field theory, and I would say Greg Yang's work also have some flavor in that direction, like using mean field analysis to find the scaling, how you should scale your parameters, learning rate and stuff from small models to large models. But one thing I think missing from the current framework is that emergent abilities is a discrete structure, and that's completely off equilibrium, so to speak. And mean field theory are like those equilibrium systems. So I think what's missing in the current theory is now we need to introduce some off equilibrium, variables so that we can have a broader scope of the theory. I personally don't know how to do that yet, but maybe we can borrow some literature from condensed matter physics, where you have some kind of quasi-particles, and that can effectively describe off equilibrium phenomenon, and maybe model this, a quasi-particle is like a quanta or like the emergent ability or subnetwork, any name you would like that to be, and to model the whole system as interacting particle system, something like that. That's the picture in my mind, although I don't know how to write down mathematical equations. But I feel that maybe that's the way to go to augment current mathematical framework for deep learning. Yeah, that's my picture.
Okay, thank you. So maybe Richard also can come on this from the practical perspective, because you trained the large language models, so in the complex, right? How can you more efficiently train such models? Maybe you can provide some advice.
For a good model in practice, there are several elements. First one is the better data. Data is always the most important thing. So the better data, the larger data, and the better quality of data. So diverse. And one way to measure the data quality or the data diversity is that we can model, or we can leverage all the knowledge of the human. So you need to do some filter, and you need to crawl all the data and different kind of data about the web, the book. So the first one is this, and second is you need to have a stable infrastructure to train model, and you need to utilize the model train efficiently. So the second way, and the third, you need to have a complete metrics and the benchmark and the test evaluation method to you can actually mean the common user thing. So the three elements leads to a better model.
Thank you. Also, Mr. Yan Ran also has done a lot of work in natural language models. I think you recently also changed your research direction, moved to the large language models, right? So I think according to your experience, you also can comment on this point.
Okay. I much agree with Richard and also Jason. And in our experience, we see that firstly, during the pre-training phase, that not more data is always the good. That means that sometimes we only need to pass all the tokens in one round, and then we can know that all the phenomena can be detected or can be measured. For example, we can see there erased some modularities before the first epoch. That means maybe the large language models have maybe emergence some abilities such as the classification, the memorization on some named entities, and then we can stop the training in the first phase and move to the second phase. Maybe in the second phase, we can do some or conduct some experiments using more efficient algorithms, such as some less parameters tuning, and it is a faster way to examine how diversity, how quality is with our data. So in the second phase of the fine-tuning, we will test our data and test our goal, whether it is good to using some more efficient algorithms. Then we move to the maybe full parameter training to finally to got our parameters and evaluate on our downstream tasks. So in this way, we can find that not all, maybe some paradigm has changed, that not more data is always good, and not more epochs we train, and not all the losses, maybe loss curve system is better. So in this way, we can have more efficient progress to obtain our large language models.
Okay, thank you. So another key question about the large language model is about how they can truly do reasoning, right? So it depends on how can we define reasoning, because I'm doing the causal reasoning. We test the large language models are different causal reasoning tasks. We observe that they do not do anything about the causal reasoning. So, but for the logical reasoning or mathematical reasoning, they maybe show some good performance on different tasks, right? So I think this is a very active fields we can discuss on this point. Yeah, so maybe Jason Wei also mentioned that, right? So because you have the lot of experience to training the large language models and investigate the large language models in the OpenAI and Google's, maybe you can provide some valuable experience on this point.
Yeah, I think this idea of large language models being able to do reasoning is maybe taken for granted now. But at least, like, say, 3 years ago, many people were very skeptical that scale would ever unlock the ability for large language models to do true reasoning. So, maybe even as soon as in like 2021, you'd have papers that would fine-tune models with large amounts of data to sort of enhance their ability to do reasoning. And then very quickly, you would see that if you use the next larger language model, then you'd actually be way better than like this. You'd be way better in like a few shot or a 0-shot setting than the model from last year, which someone tried very hard to fine tune. So I think this ability to do reasoning, and reasoning doesn't just include like math word problems, but it can also include like some types of decision making or symbol manipulation. I think this ability to do reasoning has been very surprising. And my guess is that we'll see even more ability to do like very good reasoning as we continue scaling up the size of these models.
So do you think the reasoning ability is from the memorization, or it's indeed learn something about the logical structures between the data?
Yeah, I think my personal argument, maybe not everyone agrees, is that there's definitely some true generalization of reasoning. One example is you can take so large language models, if they can do a math word problem in, say, English or Chinese, maybe you can argue that they've seen something very similar to that in the training data set. But you can take something like a language like, say, Swahili or some very low resource language that occurs, say, less than 0.1% in the pre-training data. And you can ask the large language model to do math word problems in a very low resource language. And it actually is able to do that probably better than you would expect. And I think the combination of being able to do very low resource languages plus math word problems is an example of like pretty strong generalization on the language model's part to something it probably hasn't seen before.
Okay, great. So I think it's mean maybe have a different understanding on the reasoning, right, from the physics, right, the viewpoints. Maybe also have share some different perspective on this point.
Yeah, I mean, it's why reasoning emerges from large language models. I think it's a very open question. I agree with Jason. And maybe from the physics perspective, I think there are a few types of reasoning. There are like deduction reasoning that mathematicians care about, like deriving, conclusions from axioms. But physicists care more about induction. It's like you have experimental data or observational data, and you want to derive some physical laws from it, like Kepler's law, right? You just observe how the planets, their in motion in the sky, and finally you conclude that, oh, it's eclipse, and finally you discover that the periods and its like radius have some relationship, something like that. So like in our group, we did a lot of work on this, like trying to automate like physical discoveries. But one particularly interesting question for me is that whether large language models can excel at this so-called specialist models, or like to do science, do we need a generalist models like a large language models, like it can not only speak fluent English but can whatever language, but can also do math, do physics, do chemistry, do biology, all of it, or we need to fine-tune like a pre-trained model onto specialized domain knowledge. That's something I've been thinking about a lot recently. If we can have a general LLM, which maybe like I believe that for the most smart people in the world, like my advisor Max, he did research in all sorts of fields, and it appeared, so working with him is like, wow, it sounds like everything in some sense is the same. Like, yeah, there's no barrier between disciplines. So maybe in that sense, it's it's a good way to we just throw at all kinds of data, good quality data, of course, to large language models, and it will grok all science knowledge, and I see all kinds of combinations. And the way I see reasoning is more like compositional generalization, where you actually see all the concept before, but you never see such combination. But somehow you can generalize, maybe because, well, that's the most information efficient way to do it. And I think also Ilya had a recent talk like claiming that like compression is the key, like why large language models have such amazing performance, and maybe the route to AGI. And I pretty sympathize with that. I think the information perspective, and also like maybe like when you the more data you want to compress together, the more knowledge, or the more the better representation you can get from just training on the data. Yeah, so that's my take.
Okay, thank you, Ziming. I think your response brings another key questions, because in the machine learning communities, so we now do rethink the relations between the compression and also the predictions and understandings, right? Because based on the training paradigm of the large language models nowadays, it's only predict next tokens, right? So it seems, if you want to press the data to the limit, you can learn or understand the latent structures in the data, right? So I would like to ask the panelists, what's the difference, or just the same thing between the three items? So who the first? Maybe also Jason Wei be the first.
Yeah, that's a pretty good question. I guess it really depends on how you define the terms. I mean, yeah, we call it like next word prediction, and that's fundamentally the task that has brought us to learning all of this. But yeah, I guess it depends on how you define the term. I'm curious about what other people think.
So yeah.
Okay, I can say some understanding by myself. I think it depends on what kind of task. If you have a task, then we can compress data and we can denoise the noise in the data, so we can just increase the performance of this kind of task. So actually, recently, in our group, we have done a kind of design, a kind of neural network architecture. It's just like a bottleneck, information bottleneck. So we just compress the data, the input, and then we can use very few actually the input data to predict the labels. So I think in this way, when we just compress the data, then it can understand, or it can just perform very well. And then in this sense, from the outside, we can say maybe it can just understand this kind of task. So I think it depends on the task. Yeah.
So maybe maybe comment on this.
Okay, I think the compression and the prediction and the understandings are somehow interleaved in our large language models and deep learnings. And now we all know that someone, or maybe most of us have a phase that compression will leading to more wisdom, but in deeper to delve into these questions, we must to separate that how our wisdom evolves in the era. That means maybe we can only detect the labels, and then maybe find some rules from disciplines in a task, and then we can use or combine all the heuristic to solve different tasks. So the combinations is a more difficult, high-level abstraction of our wisdoms. And then now we can only see or only be sure to conclude that our large language models can detect and predict labels, but we are not sure, or we are not very confident to say that our large language models can handle or can extract the meanings, the disciplines from the data. So in this way, I think the compression is still not equal to the prediction and not equal to the understanding. Whenever we have the power to examine or to make the large language models have some awareness of what it does do, or it does not know, and make them to generalize to more compositional tasks, to maybe easily to combine their different abilities to solve our decision makings, to solve a more difficult task in our human societies. And in that day, maybe we can see that the compression is identical to the understanding. So this is my opinion.
Thank you. So, Ziming, you inspired the question, and the question goes back to you. So maybe come on this.
Yeah, sure. So, I hope I'm not obligated to resolve this question, because I think this it's a very, very open problem. So I think, so to me, I think representation, computation, so with a good representation allows you to have an efficient computation, and which in turn allows you to do, accurate prediction. That's my understanding. So I honestly, I don't have much experience in training large language models, but I've looked at some toy examples, like how neural network do modular addition. Like what neural network do is to place those numbers around the clock. Max probably have showed that in his talk. So this is a very clever representation because you can use very efficient, computation to compute the answer to make the correct prediction. So in this sense, I would say compression to me is more like find a clever representation, but I don't know how to really define what I mean by smart. Is it aligned to human intuition? Maybe not. Maybe their neural networks have discovered some, representations smarter than us. So yeah, that's what I have in mind. It's just far from being, arriving at a conclusion, I think.
Yeah, because I asking question because many machine learning people is curious about these questions because in the traditional machine learning ways they don't believe so you just can compress the data. The best prediction performance is imply anything about understanding, right? So because when you compress the data, you reconstruct the data, you also reconstruct the noise, right? So you cannot, ignore the noise about the data. So if you want to extract some intelligence from the data, you have to delete the noise from the data. So that's the reason I asking the questions. So I think we can move to the next question about the hallucination. I think many people are also interested in this question. So I think in the most of the large language models, we cannot, ignore such question because when you apply such models to the real world applications or the scenarios, you have to solve these questions. So in the current ways, I think the most teams of the companies is only collect the high quality data to solve the questions, but still follow the very traditional common user architectures. So my question is, this problem can be solved only by collect high quality data, or you have to reinvent some, fundamental architectures to solve these things. So I think Richard maybe comment this because from the industry you have some experience on that.
Practical to resolve this problem in the industry, there are several methods. The first one is you train the model with the more high quality data, and you get more knowledge. And more knowledge will resolve the hallucination and a bigger model. And the second way is when you alignment the model, you don't instead of depend on large data with the SFT methods, which can cause the hallucination because the demonstration response maybe not have the knowledge that the base model has. So when use this kind of SFT data will lead to some more hallucination. So if you use the reject sampling or you use the RLHF methods, which the response is sampled from the model itself. So it can resolve this problem, or it can let the problem not that much. Okay. So the third way is you use the retrieval augmented. So when grounding to the outer knowledge, and the hallucination will be resolved. So, but actually, it's a very challenging problem. With this practical method, we observe that the hallucination is always there. So it's a challenging problem. Okay.
Maybe Yanran also comment on this. Yeah.
Okay. I think the hallucination problem is very closely with the reasoning ability in the language models. And someone or some some possible solution besides the Richard said that maybe is to expanding the contact length. Contact length can involve better or more information for the language models to reasoning to solve the task and give his output. In that way, that large language models will have more confidence that how to use the external data, how to use the context information to combine them together to solve the task and give its output. Then it will not, it has less probabilities to rely on data other in the context to give his answer. And the context length also is a very important thing in the no matter pre-training or fine-tuning. So I think that it's very important to first define what the hallucination problem is. Maybe we can imagine or see ourselves, our humans also perform some hallucinations in our daily lives. We may recall some things ambiguously. We may rely on false misunderstandings from our daily lives. So in that ways, we do not say that we are hallucination. We just say we forgot something, we misunderstood something. So it is also kind of a sort of similar things that we have found in large language models. So in that way, we have thought that maybe it is not very important to measure the hallucination of the language models. We should make the language models to equip is the reasoning abilities. It will be more emphasized on how the language model use the information to combine the information in the context, not to maybe to guess what it may have in the context. So that's our attempt to try to resolve to solve this problem, but it's also on progress things. So we cannot promise that this direction is correct, or maybe we can finally solve this problem. Thank you.
I have a different opinion about this question. As I understand, actually, hallucination is just like a person drunk. When we drunk, that means I don't know what I have said and what I have done. So I think maybe in the future, if we want to just solve this question in essential, we must give the machine a kind of ability as self-awareness. That means the machine can know what he has said and what he had done. Actually, maybe this is the final way to solve this question.
Yeah, the and the Professor Zhang has reminded me of another method or another perspective about the hallucination. Is the key is the make the model be awareness of what it know and what it does not know. Yes. So another practical method is we use the RL method to create some to train the RM model to separate several response. The best one is and you give the correct response, and the second is you don't know and you say you don't know, and the worst one is you don't know but you say you make up the response. So if we use this kind of maybe we can train the model to separate it and become awareness of the confidence of the response. Thanks.
Yeah, Jason, maybe you can offer some personal insights on the hallucination issue.
Yeah, I think there are a lot of good ideas that people said on how to solve hallucinations. I guess the thing I think about for hallucinations is even just improving the hallucination rate by, say, decreasing it by half will have a very big impact. I think if you consider, if someone lies to you 1 time out of 10, you lose a lot of trust in them. But if it's 1 time out of 100, then it's going to be a lot more trustworthy. So I think this is actually a really important area of research because the reliability and the trustworthiness of the language models kind of depend on them not hallucinating. And I really think more people should work on hallucinations.
Okay, Ziming, what's your point?
Yeah, sure. I actually don't have much to say for this question, but I just want to. My personal feeling is that it's not impossible to reduce hallucination, and also want to point to you a nice paper that I read recently. In case you haven't read it by Kenneth Lee from Harvard. Basically, that paper says you can, there's a direction of truth in the activation space of language models, and at test time you just shift your activation function, activation vector towards the direction of truth, and the sentences generated by the language models will be truer than if you do not do such intervention. So this is quite, positive in the sense that it's possible you do some, minimally invasion brain surgery to, so to speak, to language models. You can make the language models, speak more about the truth. And it's not changing the weight, or it's not changing the model parameters. It's just at test time you inject in, you shift the activation function toward the truth direction. So that's very encouraging to me, that maybe it's not completely impossible to reduce hallucination. And and maybe the solution can be not that hard.
Okay, thank you all the panelists for the valuable feedback and the constructive advice. So I think we have to draw the roundtable discussion to the end. So I also thank all the audience for taking the time with us today. And I think be free to continue the discussion and the conversation after this roundtable discussion. Right. So have a nice day. Yeah. Thank you, everyone.
Thank you.
Thank you.
Thank you again for the wonderful discussion from our roundtable.